Hello, and thank you for joining me. You're here with Data Science Teacher Brandyn, and we're going to do a simple deep learning, simple LSTM sarcasm detection project, so NLP, using TensorFlow. Okay, so let's get started. Okay, so here we're going to import TensorFlow as TF, and we'll be using that a lot today. And because we're doing an NLP project, so we have our regular data science libraries here, just in case I didn't end up needing all of them, but it's always just good to import them. You'd be surprised how much you need these ones. Okay, so import natural language, so NLTK, natural language toolkit, and string. Okay, we'll use these for a couple little pre-processing sections in our to deal with the strings to make our life easy today. Okay, make our life simple. Okay. And I left this up here if you need to download the data set and connect it, or if you wanted to and put it right onto your Google Drive, you'd use this to connect your Google Drive, this notebook to or this Colab to your notebook. Here, what I'm doing is I have the data set in my reservoir though, so you don't need to mount your drive if you're just going to use the data set that I have really available in my GitHub reservoir. So what we need to do, just like we're going to load a regular CSV file, we need to go pd.read_CSV and import our data. df.head just to make sure it is the data that we were expecting. And we can see we have headlines and we have non-sarcastic and sarcastic. Okay, so a really important thing especially with deep learning, but it's I guess always important in data science is, well, in predictions of binary classifications or any classification prediction, is you want to make sure that you have some sort of balance, or at least you understand the balance and understand where, if you have an imbalance, where you might be suffering or why you might be suffering predictions or having a hard time predicting classes. We can see here we have a roughly even balance. They said it's not perfect, but it's close enough. We really want to get as close as we can, especially with deep learning, to be a balanced data set. So if it was off balance, we would do things to balance it out in certain ways. So here let's inspect a couple of the sarcastic and non-sarcastic lines. So here, if we're going to go df.target, so on the inside here, so df square brackets target equals to non-sarcastic, we're going to then pull the headlines of this will return the whole data frame of only the rows though that are non-sarcastic. Okay? And then we're just going to take the headline out of that and we're going to go .ilock, just get the value right out of that. And you can see CFN trumps at least in most demographic categories. Super boring, super non-sarcastic title right there. New emails, warm relationships between Kamala and Harris, big tech. That is not super interesting. Wow. And Donald Jr. gets slammed over racist bitherism. Normal type of news truth there. Okay. So look at the sarcastic ones next. I just like to do this to get a sense of what it is. There wasn't really any specific thing aside from familiarizing myself with the data at this point, right? So just kind of getting a sense for what is sarcastic and what is not sarcastic. So God urges Rick Perry not to run for president. That is pretty sarcastic. And so going through, so we'll see if we can build a model that can well, maybe not understand, but at least predict if a comment is sarcastic versus not sarcastic. Okay. So first thing we're going to do is we're going to make everything a lowercase value, so we don't have essentially double the characters if we have uppercase as well. So we'll go .str.string .lower. So very easy thing to do in pandas, just to make everything lowercase. Now for our headlines. Okay. The next thing we're going to do is using NLT and the string libraries that we first imported up above. We're going to go nlt.corpus.stop words. Okay. And if you had a different language, you could do a different language here. We're going to do English today because our data set is in English, but you could do other ones as well. And then we're going to go string.punctuation. Punctuation. There we go. I just had to figure out how to spell the word punctuation. So here what we're going to do is nlt.corpus.stopwords. Words then we're getting English, and then string.punctuation. And punctuation is going to be a list of all the different punctuations. Stop words is going to be a list of all the different stop words, things like and, the things that don't really mean very much in terms of what the context of a situation was, really just kind of unimportant words to the meaning of a sentence. And so here what we're going to do is we're going to do dot replace. So just using the dot replace right here to replace then a string, and every value in this list will be replaced with close brackets. Every value in this list will be replaced with just, not close brackets, just empty strings, so just empty quotation marks, and that will get rid of all of those values for us. So we can focus more on the meaning and the words that carry meaning in our text and our headlines. Okay. So here we're going to do, to train in TensorFlow, you don't need to do this in sklearn, but to train in TensorFlow, we need to change our target into zeros and ones. sklearn does this transformation for you kind of under the hood, so you don't notice, or you don't need to really be aware of this. With TensorFlow, with deep learning, we have to be more aware of this, and we're going to have to allow for linear algebra right away. Okay, so what we're going to do is we're going to convert sarcastic, non-sarcastic to, if it is sarcastic, we're going to turn it to 1, and if it's not sarcastic, we're going to turn it to 0. And I just returned, while I was talking, I changed the nones to return, so I'm going to return 1. If it's 0, return 0. If it's the other thing, which would be non-sarcastic. Okay, and so I'm going to apply this function that I just made, the two-binary function. I'm going to apply this. This is either going to return 1 or 0, essentially replace over my old target with 1s and 0s, depending on what it found. Okay. So here, and I'm going to get my column names here. I got headlines right here, just like put this in. And I like to think instead of X and Y, and this will come into play a lot later on when we get to more advanced TensorFlow, but it's good. It becomes almost easier to think about data coming into your model and data going out of your model. Then you might have multiple sources of data that connect at different points in your model, in your network, and then have different outputs as well. So different predictions. And you can call them predictions. I like to think of inputs and outputs. So just forgetting about all of the vowels except for the first letter. We're going to do, okay. So input and output. I usually just do my variables without vowels. It's surprisingly easy to remember them then, and a little bit shorter. Okay, so we'll do input right here and output right here. Okay, and so we're going to do using sklearn, just this train test split, just to make our lives easy today. And so I'm going to assign num words. You can change this. This is going to be how many total number of different words you can have in your vocabulary. It is a little bit not hard, but a little bit tedious to actually go about getting this count. So I didn't do it today, but you can actually find this count of the individual words in your data set. It's not super difficult, but a little tedious. Here, what we can do, I use 10,000 just to start. If you have more than that, it would just only produce values that go up to that value, or only go up to 10,000 different words. However, you can do less of that. Try and see like 5,000, see if that helps your model or not. It really will help to do with overfitting. If you reduce the number of words, your model will have a less chance of overfitting to these random kind of words that are used once or twice. Okay. So again, you can play with this. I just set it as 10,000 as just a placeholder to make sure that we don't have too many, but we still have enough. Okay. So here what we're going to do is we're going to build our tokenizer. So tokenizer equals tf.chars. So chars dot preprocessing text dot token, capital T. And then we're going to say num words, num underscore words equals to the num words variable that we just created up above. And then filter equals to this list of strings. I have this list saved somewhere, and I just usually copy and paste it in here of all the punctuation, just in case anything was missed up above. We're going to make sure that we filter it out in our tokenizer. Oh, filters, sorry, filters. Filters, don't forget the S. So num words, filters. And as you can see, these are more than one thing. These are a collection of, this is a long string, but it's a collection of essentially a list of these string values. Okay? And then we're going to go fit. On the next one, we're going to take our tokenizer and go fit underscore on underscore texts. There we go. And going through that. Now then we're going to go our word text, our word index to get a reverse word index so that if we needed this, we could pull back essentially out of our predictions. We didn't use this today, but it's good to understand how to do this because you will essentially want your predictions to be able to turn back in from the numbers that they're predicting into, what they are. So here what we're going to do is we're going to go tokenizer and we're going to go word underscore index. Okay. And then to make the reverse word index, what we're going to do is we're going to go, let's actually start with the second set of square brackets. We're going to go for key underscore value. So what we're doing is we're giving it the word index, which is a dictionary, and we're going to go items, which turns that dictionary into a list of tuples. From that, what we're going to do is we're going to turn our value. So we're going to take our key and value pair from our dictionary, and then we're going to go essentially just reverse those. We're going to go value key or key and value in word index. So you have the reverse of this. And we didn't use this today, but this is good to know because you'll need this in so many locations in NLP, especially when you're dealing with predictions and kind of converting your predictions back into real words. So this is just good. And this is a list comprehension. Again, for key and value, do this. So do value key for key and value in word index dot items. We're going to then get our word index though, and we're going to do this, and we're going to get our vocabulary size right here. And this is what we'll use today. So, okay, so we'll get our word index here. What I'm going to do, my text to sequence, I'm going to take my tokenizer and I'm going to go tokenizer. And then here what we're going to do is I have my text to sequences. So I'm going to go texts to, and here we have my input train. So just our input data, and this is going to kind of convert it to a list of numbers. Okay, and then here what we're going to do is a list of numbers that we can then put into our model. Okay, but it's going to be a different amount for the different number of words. It's going to be a different size list that we'll have to deal with in the next section. But so we're going to again go tokenizer dot texts to sequences. Okay, just make sure they're plural for both of those. And then we get our input train and our input test. Again, just keeping the same variable name as we go through. I'm going to get the max length. Which one of these is the longest, right? Just so I can have an idea of how long. I can minimize this, but how long is my maximum value so that I can, when I pad the sequences and I make all of these values the same one, I know how long my longest one is to make them all the same size. Okay? To make especially my train and my test the same size. So here what we're going to do is, if you haven't done this in a while, they have changed this in the newer version. So it used to be pre-processing text pad sequences, but now it's utils pad underscore sequences. Okay. And then so we're going to do that for the train, and then we're going to go tf dot utils. I don't need to do that twice. And pad underscore c. Okay. There we go. Pad underscore sequence. Same on that. And so we have now they're all going to be the same length instead of kind of the different depending on the title. So sequences turns them into a list of words, and then padding makes them all the same length of words. Okay. And that's why I need this max length up above. Okay. The next one, so we're going to get into our modeling section. So we're going to use, I like to make my architecture, I like to set the variables that I'll be using inside my model up above, just so that I can look at this and change it and stuff. I don't have to kind of analyze, go deep inside. This is very small, but when they get big, it's just easier to kind of have a list up above. You might not feel that. I think you will eventually, if you don't now, you'll eventually feel that it's easier to see these variables up above here. And you might use them at several times later on in anything. So you don't have to have so many. If you want to make a change to one, you can make a change up here that will change everything down below. And it's a little bit easier to go. So, so I'm going to have my recurrent neurons be 4D. So this will be in our LSTM layer. My recurrent activation function will be a tan h. So tf.nn.tan h. So the hyperbolic tangent, which works well, okay? And especially for recurrent layers, I find. What we're going to do is dense 40 neurons, dense act, so DNS act equals tf.nn dot ALU. So I like ALU for dense layers. It's one of my favorite ones. Here, what we're going to do for optimizer. I find one of the best optimizers for NLP is usually Atom. It's a good general purpose one, but it is a good one for that as well. For the way we're going to build our model, we're going to be doing a binary classification. So it's basically just a logistic output. So with this, what we're going to do is we're going to do binary underscore cross entropy. So binary cross entropy. Okay. So that's going to be our parameters, kind of our hyperparameters that we're going to be defining. And then epochs. Okay. So the next level, so we'll actually define the architecture, the layers of our model. So tf.keras.model sequential, so our sequential model. We want tf.keras.layers.embedding. So we're going to do the number of words that we define up above, our embedding dimension, which is right here. We're going to use 40 as well. And then our input underscore length is equal to the max length that we got up above. And I just have the title here, max length. Okay. What we're going to do next is we're going to do in the next layer, we're going to do tf.keras.layers.capital LSTM. Okay, it's a recurrent layer. We're having our recurrent neurons and our activation with our recurrent activation. Okay. So you could do LSTM, you could do simple RNN, GRU would also work here as well. Just see which one works best. I usually LSTM for text is a pretty good. It usually works good. I find simple RNN is a good recurrent layer to use on maybe like spreadsheet type of data, financial data. Sometimes it works better than the LSTM. LSTM is really good on text though. Okay. So we're going to do tf.keras.layers.dropout. This is important just to help prevent overfitting. And in the next one, tf.keras.layers. And the last layer, we're just going to have a dense layer. And we're going to be outputting one neuron. And our activation on this last layer is going to be tf.nn.sigmoid. We're going to then compile, so model.compile our model. This is where we're going to tell our model what to think of the loss, what to decide is incorrect, and the optimizer to help it slide down the gradient a little bit. So the first thing we'll define is loss equals ls, which is the loss we defined up above. And then optimizer is the optimizer atom that we defined up above. And then just because binary cross entropy, sometimes, especially the classification problems, especially when we're dealing with a multi-classification problem, the entropy value is just not necessarily easily understood and stuff. You want to get a small one, obviously, but it is better to consider accuracy, a little bit easier for us humans to understand. So I always get when we're doing classification metrics, and I want to look at the accuracy, so ACC. Okay, so define that. And then I'm going to fit my model. And just notice that here I'm assigning H for history. So history or H equals model.fit. I'm going to go input train, output train. So X, Y. I'm going to define my epochs. Okay. And then I'm going to define my validation underscore data. Okay. I'm going to have my inputs in my test input and my input test. Or sorry, input test and output test. Okay. So my test data. Okay, so we'll train this. And while this is trained, this won't take too long. It's a very simple network here. We did just 40 by 40, really nothing super big. It worked well though. It's good to start simple and then kind of build up. So I started fairly simple. See if you can make it simpler and then see if you can make it a little bit more complex. So it's always good to start simple with neural networks because you can get super complex. But if you start complex, it's hard to understand why your network is working well. So to plot this history, so I'm assigning this to history. So I'm going to go the easiest way. You can do this in many ways, but this is definitely the easiest. So we're going to go data frame. So pd.data frame. History is the history object that I created up above. History.history. So h.history. And this is essentially going to, this is a dictionary that comes out of this, and it fits really nicely into a data frame. And then if you just go data, essentially data frame dot plot, it will just plot these values as well. Okay, and now that our model has trained, so I'll finish the last epochs, and we had a training accuracy of 99%. Our validation accuracy is only 88. We got up to 90 or so. So there's still definitely room for improvement for sure. But this is very, very simple in this network. So we can expand by adding more dense layers in between this. We could try different LSTMs, different optimizers, different, well, our loss is kind of what it is. We could try different embedding in dimensions. I did experiment. I think this works good for how simple it is. But again, you can definitely kind of almost unlimitedly more complex, and you will find that it does work better, but it is hard to find that complex architecture that works well. So it's a good starting point, and for a simple LSTM project, and we'll get more complex as we go on from here. So enjoy. Thank you for joining me today, and I will see you next time.